Okay, great. Hopefully you can see that and hear me okay.
Yep.
All right, so this is the presentation that I gave at SETI conference in Australia probably 3 months ago now. And it's about, as you can see, requirement schemas for large multidisciplinary projects. So I'll dig into it, and hopefully there'll be plenty of time for questions at the end. This is me. I am a technical principal with WSP, leading the rail systems engineering team here in New Zealand. Importantly, with reference to this presentation, I was previously the requirements manager for the Link Alliance on City Rail Link, and I'm currently the systems engineering manager for the terminals designed for the Inter-Islander Resilient Connection, which we'll be using as examples as we go through this. So to dive right into it, I've got a few definitions up front so that we understand what I'm talking about. They're relatively basic. So hopefully you can all follow along. What I mean when I say schema, ontology, or meta model is really an entity relationship attribute type database. And I'm talking about these things interchangeably, and I'm talking about a level above what you might be implementing stuff in your project. It's the description of the structure of the thing that you're implementing as a database. So as an example here, if we've got a meta model that has two entities in it, person and check, they might have a relationship that says a person performs a check, and then each of those entities might have attributes on them around their name, their role, the title of the check, or the result of the check. So that would be our meta model, and then conforming to that meta model, we might have a system model that would include one or more entities from our meta model and one or more of the relationships out of our meta model. So you can see that here we've got two class person, two class check, and they've got specific names in our model, and they've got specific relations between them, and they all conform to our meta model. And of course, they can have attributes as defined by our meta model. So that's what I mean when I say meta model or system model in this presentation, and we can argue about differences between ontologies and schemas and meta models afterwards if we want to. To put that in a broader context, this is a structure that I sometimes like to use. So what I'll be talking mostly about here is what I've termed here an organizational meta model. It's a meta model we've used across a number of different projects within WSP, and I'll be using examples from two specific projects, which will be project meta models. And so we use a general template within our organization and then apply it on projects to form a specific meta model, and that meta model structures the actual project model. And we could also have a sort of abstract system model that we might reuse between projects as well, maybe for a ferry, generic ferry, or a generic rail station or something like that. And there are higher level things we can talk about, frameworks and frameworks for frameworks as we go up in that hierarchy, but we're not going to get involved in that here. And as a sort of key concept and a background to the way I like to structure things, and what we're going to talk about here is various different pros and cons to different structures within a meta model, is I like to store information in linked entities rather than attributes of an entity. So what I mean by that is, from our previous example, we could have had an attribute for person that was checks performed or something like that, and then just a big list of all the checks that John or Cara had done. I would prefer to see those things as two separate objects in my model rather than attributes of a single object. And in my mind, that allows better extensibility, it allows better reuse, and therefore promotes more consistency. You can sort of get halfway there with things like enumerated attributes, where you perhaps could select from a list of possible checks that a person could do. But then if we want to add a new type of check, that would require editing our overall meta model to add that into our list of possible enumerated attributes, rather than just adding it as a new check object within our actual system model. But of course, there is a trade-off here between flexibility and complexity, and I'm erring more towards a more flexible model, but it makes my meta model slightly more complex. So with that background out of the way, let's talk a little bit about the two examples. And this is something I'm not going to dwell on a lot, because as Kiwis, we know more about these projects than my previous audience in Australia did. So most people will be familiar with City Rail Links, so I'm not going to dwell on it too much, other than to say that it's an ongoing project, which we as WSP have been heavily involved with as part of the Link Alliance with a number of other organizations, some of which are represented in the audience today. Specifically, as we're interested in it from the perspective of tonight's presentation, City Rail Link Limited, as the client, have mandated a systems engineering approach. They've stated that it's a requirements-driven project, and they've specified the project with a hierarchy of different requirements, some of which we'll dig into in a moment, but you can see from the numbers there are quite a lot of them. It's heavily using requirements to drive the work that gets done on City Rail Link, and the use of DOORS Next Generation has been mandated for requirements management. The Link Alliance is delivering its work split across a wide variety of different packages and design disciplines and subcontract works, and that's really coming back to the presentation title here of multidisciplinary. That is a lot of different disciplines and a lot of different packages of work to manage as individual deliveries and make sure they all tie together and that they all sum up to delivering an overall functioning rail link. And the work that we're talking about here in terms of requirements is all adding together to deliver that. A second project that I'm heavily involved with currently is the Inter-Islander Resilient Connection across the Cook Strait, from Waitoa in Picton to Kaifara in Wellington. And you can see from the diagram we've got here, I should say that this is straight off the iReX website if you want to read more about it, and the previous details are all from the City Rail Link website as well. So there's a lot more information out there if you're particularly interested in either of these projects, but I'll put this one in here just to show the variety of different assets and systems and different disciplines that will be involved in delivering this type of a project. So we've got rail in there, we've got road in there, we've got ships in there, we've got buildings in there, we've got a lot of civil engineering in there. There's really quite a big variety of disciplines involved, and again, split across many different packages of work. And I should mention in the context of iReX that this is work being delivered by WSP and Jacobs, and with systems engineering support from Shoal. So to put a few numbers to that, again, we'll dig into these in a little bit more detail. They have a set of minimum requirements specified by KiwiRail as the client, again, mandating the use of DOORS Next Generation, and multiple design packages, multiple design disciplines, 3 major areas of land, marine, and building. And we'll dig into a little bit as to what we mean by minimum requirements. And this is a term that I'm not sure how widely it's used, but I see it on quite a lot of infrastructure projects, sometimes project requirements, sometimes other variants on that theme, but they're typically the client's requirements. They're often a mix of both technical and process type requirements. They're often related to higher level statements, but not necessarily fully traced. They're almost always written by subject matter experts, but not typically by requirements experts, meaning that whilst they are usually sensible in what they're asking for, they're not necessarily using an INCOSE certified requirements syntax or to INCOSE requirement quality standards. So there's often duplication in there because there's multiple different experts written their own sections. There's statements in there that are often difficult to verify, and there's often an inconsistent level of detail. And they form the stakeholder requirements for the project. Ideally, they're based on a complete operational concept, as we know from our sort of good INCOSE requirements delivery definitions, but typically on this type of project, the operational concept is never fully complete until we're quite close to going into operation. And because of the long timescales involved in infrastructure construction, some aspects of the work need to start really quite early, often before we've really developed a full understanding of how we want to operate things. So there is a bit of backwards and forwards needed between what's in our requirement set and what we actually need to operate the project. And that sort of comes into play with these things as well. So there's three major areas I wanted to talk about in terms of what we want the schema to do. The first of which is requirement development. So as the minimum requirements that we get given as a delivery partner are typically contractual, they need to be owned by the client. So any kind of change to them needs to be approved and made by the client party, which leads to the need for us to develop delivery party type requirements, which typically is a decomposition of the higher level client requirements. So we get the nice requirements hierarchy that you'd all be familiar with. And I've just called them delivery requirements here. We'll see that we've used different terms for them on different projects. But what we're really looking for is alignment of those delivery requirements at a level of detail that's relevant to the systems being delivered. And it's also an opportunity for us to make quality improvements where we need to clarify exactly what a minimum requirement means. We can do that in our delivery requirements set, and we can also add in derived requirements. And typically those will be coming from a variety of different sources, which we'll talk about in a moment. But the need to have these two things separated is usually allowed for in your requirements management tool, and DOORS Next Generation, which you've been using on the two example projects here, allows that quite nicely. So we can have our minimum requirements in a client area of the tool and our delivery requirements in a delivery area of the tool. And that allows us to make traceability links between them, but importantly, delivery parties can't edit client requirements, clients can't edit delivery requirements. But we have visibility and we can manage user access rights to have good visibility of what's going on. So on City Rail Link, it's a little bit more complicated than that. We have a hierarchy that has been defined by City Rail Link Limited. So we have a set of fit for purpose statements at the highest level, a set of functional requirements below that, and a set of design manual requirements below that. And it's the combination of functional requirements and design manuals along with a load of supporting requirements that form the minimum requirements that the Link Alliance needs to deliver against. It's not quite as simple as that either, because there's some quite complex traceability in the CRL requirement set. So whilst that hierarchy does exist, there is also traceability from the design manual requirements direct to the fit for purpose statements. And there is a need for us as the Link Alliance to verify we've also met the functional requirements as well as the design manual requirements. So we get this slightly more complex sort of traceability between the different objects in our schema. But it can be done, it works relatively well. we can make all of those links and end up with a consolidated system requirement set at the bottom there that has complete traceability to the minimum requirements above it and vice versa. So we can demonstrate that all of the minimum requirements are covered by something in our system requirement set, and then we can deliver against our system requirements. So our system requirements in the Link Alliance case, the majority of them come from the minimum requirements, but we have a number of derived requirements coming from other sources. Outside of our requirements management tool, they come from interface management, human factors, RAM, and quite a bit of design development. But also, we've used the doors tool on CityRail Link to also manage our safety and design process, and thereby trace our system requirements to safety controls, which trace to safety hazards identified through the safety and design process. So that gives us quite comprehensive traceability, and we can see where all of our system requirements have come from, even if they're not traced upwards to a minimum requirement or a safety control. We have a source attribute that tells us where in an external register they might have come from. So on iReX, we've got a similar but slightly different situation. We've got our minimum requirements. They should trace upwards to a set of higher level requirements, but as we mentioned before, concept operations is still somewhat in flux there, and that traceability is not complete as of yet, but we do have a relatively complete minimum requirement set. And the requirements at the delivery level we've termed asset requirements, and they have complete traceability up to the minimum requirement set. As I mentioned previously, we have two terminals at iReX, Picton and Wellington, and the requirement set, or the minimum requirement set for each of them, is quite similar to one another. So we've introduced this extra link on our asset requirement, which is this similar to link, which allows us to see what the counterpart requirement between Picton and Wellington is. And that allows us to do things like impact assessment. If Picton is requesting a change or a departure from a specific asset requirement, then we would like to know, does there a similar requirement exist for the other terminal, and do we need to depart from that one as well? And it's usually quite likely that we do. If we can't meet it in one place, there's a good chance we're not going to be able to meet it in the other location either. And a lot same goes for making minor changes to the requirement set or understanding our compliance with them. Often if we're non-compliant in one area, there's a good chance we're non-compliant in the other. And it's an ongoing process, but we have quite recently added derived requirements into our asset requirement set coming from human factors, from sustainability. It's an interesting one coming out of our ISC credit score. We need to achieve an excellence rating with respect to sustainability ISC credits, and we've traced our asset requirements to those credits where they've come from. And also consent conditions, which effectively form requirements that we need to meet in both locations to keep councils happy. So those are part of our requirement set as well. The next area I wanted to talk about is requirement allocation. And often people talk about requirements having owners, and what people mean by the ownership of a requirement tends to vary. I prefer to think of them as being delivered by someone. And you could think about the requirement being delivered by a discipline, but in actual fact, on the type of projects we're talking about here, disciplines deliver packages of work, often multiple packages per discipline, and it's more accurate to talk about what package is delivering each requirement. But again, it's a little bit more complicated than that, because if you look at your ISO standards, a lot of them will tell you that requirements are delivered by a system element rather than a person or a package. So what does that mean in the rest of the context? Well, a system element, I would say, is delivered by a package. A package has a discipline that's responsible for it, and that therefore means that a system element falls under the expertise of a certain discipline. And what I like about this as a model is that it puts systems at the heart of what we're talking about. It's quite easy, and I've seen it on a number of other projects, to deliver requirements management as almost an isolated thing. Say, okay, here's a set of requirements. This is one's for you, that one's for you. Tell me if a design meets them. And then as an almost totally separate work stream, talk about, say, interface management and say, you tell me what your interfaces are and we'll manage all these interfaces. And then as a separate work stream, talk about system architecture and draw out a system breakdown structure. By putting systems into our requirement schema, it means we're actually talking about the same thing. And those system elements are our system breakdown structure. And between those system elements are our interfaces. And it brings it all together. And we'll talk about at the end the concept of model-based systems engineering, and then the fact this is the direction we're trying to move in. So what does that look like on City Rail Link? Well, as we've said, design package delivers a system, and we can get our system breakdown structure by saying systems are part of other systems. And the system requirement is achieved by a system. But what we found when we started off doing this is that requirements tend to vary in what they're talking about. Some of them apply to all of the locations. And of course, on City Rail Link, we're delivering 2 brand new stations, one almost completely redeveloped station, quite a few changes at Britomart, sections of tunnel in between all these stations. So we've got a lot of similar but slightly different locations. And other requirements apply to, some of them will apply to the location, some of them will apply to everything in all the locations. So what we've done to address this is separate the concept of types of system from specific instances of systems. And what that looks like here is we've got a design package delivering specific instances of systems, and each instance is of a more general type of system. So we've effectively got 2 system breakdown structures. We only really manage the breakdown in the type structure, but that allows us to be able to link requirements either to a specific instance or to a general type. So for example, we may have a requirement about the length of platform 1 at Out Here Station, and we might have another requirement that is about the loading capability of all platforms at all stations. What we didn't want to do is duplicate that loading requirement 10 or more times and apply it to every single platform at every single station, because that would have exploded the number of requirements that we needed to manage. But we needed some way of being able to apply it multiple times. And so this is the way we came up with to achieve that. And so what that means when we come to verify that our packages are meeting our requirements is we have to trace through this structure. So for a specific package, in order to find what requirements go with it, we would first of all look at all of the system instances delivered by the package and all of the requirements that go with them. We would also look at all of the instances and what types they are and what system requirements go with those types. And we'd look at all of the instances, all of the system types, and all of the parents of those system types and what requirements go with them. because our platform example, we might have requirements about the loading on all platforms, but we might have a more general requirement about all structures or everything made of concrete or something. So those general requirements would be linked to something higher up in our system type breakdown structure. So we would gather all of our system requirements based on this traceability through the database. So that system breakdown structure I'm talking about there on CRL is managed indoors. We have various levels of hierarchy. You can see a lot more instances than types, as you might expect, which ends up with many instances per package, depending on the package. Some are very small, some are very large. And then we can work up a number of requirements for each package based on querying that database. So we've done a different approach on iReX. We obviously have two terminals that are similar, but we don't have as many duplications of instances as we do on, for example, CityRail-Link. So the approach we've taken on iReX is to have our package linked to our assets, linked to our asset requirements. But we've made the decision that an asset requirement only goes with a single asset. We still have our breakdown of assets with this built-in relationship, which allows us to decompose it. But because we've only got a single asset per asset requirement, that means we have to duplicate our asset requirements for as many assets as they're relevant to, which pushes our asset requirement numbers larger. But it makes the complexity in our database a lot less. So we don't have to go through the complicated traceability to find all of the requirements for a package. All of our requirements only go with a single package. So it's this trade-off between complexity and quantity. The other thing we're doing on iReX, as I mentioned, is interface management. So we have our interfaces between our assets, and we also will be quite soon deriving requirements for our interfaces. So that ties in quite nicely in the structure. The last thing I wanted to talk about was verification. And before I get into that, I want to clarify what I mean by that, because in my experience, there's quite a lot of variation in what people mean when they say verification. Same goes for validation. And the way that I typically like to clarify this is by talking about what are we verifying against. So we could be talking about verifying our design against our delivery requirements. We could be talking about verifying our delivery requirements against our minimum requirements. We could be talking about verifying our minimum requirements against our stakeholder requirements or against quality standards, or we could be verifying the built system against the minimum requirements. And we'd be using the term verification in each case, but what we'd actually be doing in practice would look similar, but quite different. And what I'm talking about here is really just this first one, verifying the design against the delivery requirements. But we can maybe mention at the end some of these other options and how we might build those into our schema as well. So design verification against requirements. I've seen quite a few projects where it's not been done early enough in the project lifecycle, and somebody near to the end has suddenly realized that it needs to happen. There's a whole bunch of requirements. Hopefully the design meets them. Quick call in the systems engineers. And that is problematic because we end up with system engineers who are not experts in all the relevant disciplines, sitting down and trying to tick off designs that they sort of understand against requirements that they sort of understand, and going through this very sort of manual process of verifying whether the design meets the requirements. And then, of course, it doesn't. There's some requirements that have been missed, or the design's been tweaked in a certain way. Whose fault is it? Well, why is the systems engineer telling us this is wrong? Well, that design's fine. The client must be wrong. And so it breeds this sort of problematic relationship, and it's not actually doing the job early enough to catch the risks, that we mitigate the risk of things going wrong. So what we've tried to do on these two projects and other ones we've been involved with is move this process both earlier in the life cycle and spread the load of it across more people. So the design teams need to be engaged in the process, and they need to be engaged in the process early enough. So we've placed the responsibility on the design teams to verify that the design meets the requirements, which they should be conversant with the requirements. They should be conversant with the design, and they should know absolutely whether the design is meeting those requirements. So typically we do this in a staged process along with the design development, and we build up to a complete set of compliance at the completion of the project. So in a general sense, what does that mean? Well, it means that our requirements need to have some kind of compliance check made against them to verify that the design meets them. So we can say there's one statement per requirement, and we can group them into what I typically refer to as a verification register. If you look into the standards, there are lots and lots of 4- and 5-letter acronyms for this, usually R's, A's, T's, M's, some kind of matrix, some kind of verification matrix, allocation requirements, verification. There's all sorts of combinations of letters that make up something that is a list of requirements and compliance statements against those requirements. I'll just refer to it as verification register. And we might want to have each of those compliance checks to say, do we comply, or do we not comply, or do we not know yet? Why do we think we comply? Where is the evidence that we comply? Who is it that's saying that we comply, and has it been checked by somebody? And we could break those out as separate links in our database if we wanted to make those separate objects in our meta model. What that looks like on City Rail Link is we have compliance statements that verify that we've met our system requirements. And of course, the system requirements trace to the minimum requirements, which means we can be somewhat confident that we've met those minimum requirements. Unfortunately, it's not quite as simple as this, because of the way that we've developed our model for CRL. We have potentially the same system requirement applying to multiple instances, or multiple instances and multiple packages. So to make sure that we understand exactly what we're talking about, we link our compliance statements both to the system requirement that they're verifying and the system instance that they're verifying. So we might have one package being compliant with a requirement and the same requirement be non-compliant on a different package. And it's important that we understand which package is compliant and which one's non-compliant. On iReX, it's a lot more simple because we've got a single package per requirement. We don't need to make that link. We can just link our compliance statement direct to our asset requirements. So to pull that all together and summarize, on CRL, this is what our meta model looks like, or at least the bits that I've covered here. There are bits we've not talked about. But that's the overall sort of view of how it works. on iReX, it's a bit simpler, but that's a trade-off that we've made in terms of quantities of requirements. And a note that I promised to come back to on model-based delivery. So any of you that are very familiar with model-based delivery will be looking at this and thinking, yes, this is a model-based approach. Whether we want to call it model-based systems engineering or not is largely semantics, I think. I think having a well-defined schema adds value to your project, even if you're not taking a comprehensive MBSE approach to delivery. We've got multiple different tools in use. We're using DAWs on both of the projects we've used in examples here. DAWs isn't what you might term an MBSE tool, but I think we've shown that you can use it for more than just requirements. It's not perfect, but it is relatively easy to get buy-in to. And extending the use of a requirements management tool into system architecture or system element management or interface management is sometimes easier than introducing a whole new tool or using a tool that's sort of less built around requirements. So that's the sort of strategy we've been taking, is sort of pushing towards a more model-based approach to delivery without explicitly labeling it that, and extending the bounds of what's being done in the requirements management tool. And I think we're sort of getting to the limits of that, and certainly been pushing the limits of what DAWs can cope with. But it is working on these two projects, and I think there's some merit in this sort of approach. So to wrap up, even though you can look at the standards and say, okay, this is how you do requirements management, actually, when you dig a little bit deeper, there are a lot of variations in the design of requirements management schemas. And depending on your project, will depend on what kind of schema will work best. And I think choosing the wrong one could have quite a large impact on your delivery. And what you're seeing here is the result of iterative changes and improvements, some of which I've mentioned, some of which I haven't, across both of these projects. But defining that schema up front, even if you do have to iterate on it as you develop, I think is critical to good quality systems engineering delivery. And as I've mentioned, these decisions you're making on your schema design are often a trade-off exercise between things like flexibility and complexity. What I've not talked about here, but is most definitely included in both of these projects, is things like change and departure management. So we have all of those linked and tied into our requirements within our schema. The management of standards and abbreviations and defined terms that appear throughout our requirements set, they're all in there. Test activities and the capture of evidence against test is a big major area that CRL is getting into at the moment, and that all needs to tie in and demonstrate that not just the design is verified against the requirements, but the built environment's also verified against them. Functional and operational modeling and the linkage of all this into building information modeling is a big area that I'm quite keen to explore further and develop better in future projects, because really this is all part of digital engineering delivery. And that's it from me. Happy to take questions or clarify anything that anybody didn't understand.
Thanks, John. That was an excellent presentation, and even if I saw it before, I think I learned more the second time through. I'd be really happy to open it up for questions from the group. If you wouldn't mind using the putting your hand up tool, so that we can call on folks one by one. As folks start organizing their thoughts, I wanted to touch on a subject that you said deliberately isn't included in this, but when you talked about having made a choice in structuring your schema to duplicate asset requirements across the requirement set, how do you handle change propagation in the event that a trade needs to be made? And if not, how do you handle, then perhaps how might you handle such a situation?
Are you asking about changes to the requirements or changes to the design?
Yes, both. Sometimes design, a design that is thought to be feasible at the point of translating that into something in the real world falls apart, and we have to decide what happens. But also, I would expect that if there was change to design, that would ripple up to be reflected in requirements as well. Maybe that's an incorrect assumption in my mind.
No, I think that's reasonable in some cases and not in others. Changes to requirements, we would typically expect, if I jump backwards to my first slide about requirements structure. So we have our client requirements and our delivery requirements. I would expect that changes need to be made to the client requirements. So if we as iReX or iReX terminals design, or we as Link Alliance design delivery found that we couldn't meet a minimum requirement, we would raise a change request or a departure request against the minimum requirement. And as part of that change request, we would need to understand what was impacted, and there'll be an impact assessment. So we would start with the delivery level requirement and say, okay, this package of work can't meet this delivery requirement, which means almost certainly we can't meet the minimum requirement that it's come from. What does that mean if we change the minimum requirement? So we can look upwards and say, we want to change this. What does it also trace to? So if we've split our delivery requirement across multiple packages, we will look upwards and say, oh, this actually traces down to 3 more packages. So if we ask to change this, do we then become non-compliant in these other packages, or do we need it to change across all the packages? And that might be where we decide actually we want a departure from it in this one specific case, rather than a change to the overall requirement. So that ability to sort of trace upwards and downwards really helps with that sort of impact assessment. And also on iReX, where we've got that similar to link between the different terminals, we've also been trying to maintain that where we split the asset requirement between multiple packages. So that also assists us with that impact assessment to be able to say, oh, there are 2 or 3 other similar requirements to this that might be impacted by a change request. Does that answer your question?
Yes. Yes, it does. I don't want to, I've got more questions, but I would open it up to anybody in the audience.
Thanks, John. It's Bruce here. If we could just go to your system instances. Where is that?
Under allocation.
Yeah. So in the
yep, the next one, I think. There we go.
Yeah, there we go. Okay, so you have this schema over here. I'm guessing that's something in the sort of electronic side of things where we are sitting at the moment, we could probably use that to get rid of the repetitiveness of things like bit requirements, bit and test requirements. There are a lot of generic requirements there. I think might lend itself to trying something like this.
Yeah, I think there's it depends on the domain that you're working in. Obviously, some cases, if you're just producing sort of one-off products, then your system breakdown structure will just be all instances. In other cases, if you're producing whole sets of things that are very similar but slightly different, then your system breakdown structure will just be all types of things. I think there are certain situations in between that where it's beneficial to split the two, and I think CRL Link's a good example of that, where we're producing we've got a lot of requirements for specific locations, but also a lot of requirements for general things. And it sounds like you might have a similar situation. Yeah,
something like we've got a set of products, and there's a whole lot of requirements that are very similar in terms of for example, the bit. They're all microprocessor based, so there's a lot of commonality there.
Yeah, and it was interesting at the SETI conference, there was 2 or 3 other presentations which touched on similar topics to this, where they've found similar use of splitting things between, are we talking instances and types, and the terminology varied a little bit, but there was actually people using, we developed this on the project really, but there was people using almost the exact same terminology for coming from Holland and all sorts of other places.
Yeah, I think this certainly gives me food for thought about maybe going in the future with defining requirements and setting up schemas and so on.
Great.
Yeah, thanks. And well, I mean, I'm working on a particular product at the moment, and there are 7 variants of it. So this concept of a system instant would actually be quite nice.
Yeah,
you spread it across them. Thanks a lot.
No problem.
Anybody else want to jump in? I'm looking at the mic mutes in the chat. If not, John, I wonder if you talked pretty extensively about verification, and thank you for defining what you mean by verification. It means different things to different people in different contexts. So it's useful to have a common definition. Would you comment on validation and how I like to think of verification as checking to see whether something was implemented in accordance with the recipe. But validation is determining whether the actual end item is, fit for purpose, adequate, good for, suitable for use. I wonder if you can comment on an approach to validation within this particular either these, if not these projects, then at least broadly how you might leverage schemas like this to support that.
Yeah, I think the common definitions of sort of the difference between verification and validation, building the right thing versus building the thing right, are useful. I sometimes find they're a bit trite, and it's very easy to say, oh yeah, that makes sense, and then you come to saying, well, I've got this requirement that's come from a document called functional requirements, and what I'm doing is measuring the earth resistance to ground at this point. Am I doing verification or validation? I don't know. It's quite difficult to say in practice which is which. So it's probably more important to say this is what we're calling the thing, and everything that we're doing in this place is what we're calling validation, and this is the way we're going to be doing it. To try and answer your question, validation in the sort of schema that I'm talking about here, if we jump to the end, I would say for CRL, we've obviously got our fit for purpose statements at the very highest level. Ooh, I have to here. We've got the fit for purpose statements at the highest level. And we've got design right at the low level. And then up the right-hand side of the V, which I don't have a good diagram to show, in this set, we have integration. So we're building all of our systems. And at some point, we need to check, does what we've designed or what we're building actually meet our fit for purpose statements? And that, I would say, is definitely validation. Whether checking the design against the functional requirements is validation, whether checking the partly integrated built environment against the functional requirements is validation, open to discussion, I suppose, but there's definitely an exercise needed to confirm that, first of all, our design meets the fit for purpose statements and our final built environment meets our fit for purpose statements. And both of those, I would say, with validation. How do you go about that? Well, I think in practice, it's not necessarily quite so much of a requirements management task on infrastructure projects. We obviously have a lot of sort of non-systems engineering legacy testing and commissioning type policies in place. The client is always involved and reviewing the design. So a lot of that sort of what you might call validation is happening inherently as part of the overall design review process. So whether you pull specific parts out of that and say, we're doing validation here because the design is being reviewed in an interdisciplinary setting, or it's being reviewed by the client, or it's being accepted by a technical advisor, or whatever you want to call it, I think it is open to how you define the terminology on the project. But obviously you do definitely want to be doing all of those things.
Having fit for purpose statements really makes it more clear how you would go about establishing that something is the right thing to do at incremental steps along the way. That's for sure.
Yeah, and I think there's also a difficulty depending on how your contracts are broken up as well. If and you know, particularly on CRL where we've got an alliancing type structure, there's some navigating on whose responsibility lies where. Different again on iReX, where we're delivering a design contract and we're not delivering construction as part of it. So whilst we might be involved in the validation of does the design meet the overall fit for purpose statements, obviously the client needs to be heavily involved in that as well. So is it client, is it delivery party? We can't be involved in the construction because it's not happening, or we're not part of that contract, or do we need to be brought into that contract to enable it? So there's a whole lot of contractual boundaries to navigate in that space as well.
Yeah, organizational complexity on top of technical complexity. Yeah. I think we've had a few folks drop off at this point, so I imagine that we're probably close to done. So if you don't mind, John, I'm going to grab the screen back. Yes, I would like to share this screen. Screen 2, click the button, should be sharing. So the link to the slides is actually embedded in this. So when folks get an email of from tonight's meetup, you'll have this available to you. So again, thanks everybody for a really successful year. I'm really pleased that we have been able to achieve what we have and really come together, coalesce and come together as a community in a way that that we thought we might be able to at the beginning of this, but we really have come across. So again, thanks for coming. Ways to connect. Really appreciate everybody's participation in the chapter activities, as well as in these sorts of meetups. Thanks again. Have a great evening. I should probably stop recording now. How do I stop recording? Stop recording.